Welcome. You are watching lecture series on electromagnetic field theory. This is lecture number 4, part 1, energy and power. So this topic, energy and power, is by far the most important topic when it comes to electromagnetic field theory. So it is very important for a student to understand how the equation of conservation of power or conservation of energy is derived. So this particular topic has been subdivided into these many subtopics, which is understanding the product E dot J, a vector identity, defining Poynting vector and density of power flow, electric and magnetic energy density of static field, defining dissipated power, supplied power, and finally conservation of power at any point or within a region, and conservation of complex power. So in this lecture 4 part 1, we are going to deal with instantaneous field quantities. So we will stop at this point. In the next part we will deal with conservation of complex power. So let's start. So what is E dot J? So the unit of electric field is volts per meter, and the unit of the current J is ampere per meter square. So when you multiply E and J together, you get volt ampere per meter cube, and volt ampere is nothing but watts. So watts per meter cube. That is why we call this as power density. Power density. Similarly, what is H dot M? So H is ampere per meter and M is volts per meter square. So H dot M is volts ampere per meter cube. So again you get watts per meter cube, which is again a power density term. So the main objective of this topic will be to write equations in terms of a power and basically derive equation for conservation of power or equation for conservation of energy. So basically if you call it conservation of power or conservation of energy, it's the same thing, because the time derivative of power is nothing but energy. Alright. Next we need a vector identity which is used widely in this derivation, and that vector identity is vector identity is divergence of a cross product of two vectors A and B is equals to B dot del cross A minus A dot del cross B. So this vector identity will be used. What we are going to do is we will replace these two vectors A and B with our electric field vector E and H. Notice that this electric field E and magnetic field H is written in scripted letters, which means that we are dealing with instantaneous fields. So let's replace this. So we will get del dot E cross H is equals to H dot del cross E minus E dot del cross H. Okay, so now we will use this equation to derive the conservation of power. Now notice this term del cross E and del cross H. So we very well know from the concepts of the generalized current that del cross E is equals to negative of the total magnetic current MT, and similarly del cross H is equals to the total electric current JT. Now if you see these two terms, here del cross E has been multiplied with H, and here del cross H has been multiplied with E. Therefore we will multiply this term with H and we will multiply this term with E on both sides. So let's do that. So we are going to do scalar multiplication. Scalar multiply with H, and here we will do scalar multiply with E. So this becomes H dot del cross E is equals to minus H dot M total, and this becomes E dot del cross H is equals to E dot J total. So all these are vector quantities. Now if you simply substitute this term and this term with this and this, we will get del dot E cross H is equals to negative H dot M total minus E dot J total. Now if you bring these two terms to the left hand side, you will finally get del dot E cross H plus E dot J total plus H dot M total is equals to 0. Let me call this equation number 2, and let's call this as equation number 1. Okay, now since we see a divergence term here, so if we do volume integration on both sides and apply divergence theorem, we will get a different form of equation 2, which will be in integral form. So let's do that. We will do triple volume integration on both sides here on equation 2. So we will get triple volume integration of del dot E cross H dot d tau plus triple volume integration of E dot J total plus H dot M total d tau is equals to 0. So now we will apply divergence theorem only on this term, divergence theorem. So what does divergence theorem says? It says that triple volume integration of divergence of any vector A d tau is equals to closed surface integration of A dot ds. So when we apply this theorem onto this first term, we will get closed surface integration of E cross H dot ds plus triple volume integration of E dot j total plus H dot m total d tau is equals to 0. Let's call this as equation number 3. Now here we are going to use equation number 2, this equation, to further move on and derive the conservation of power. So let's say I call this as first term and this as second term and this as third term of equation 2. Now this is the right time to define few terms. So first we will define Poynting vector, or density of power flux. So a Poynting vector is simply defined as S is equals to E cross H. So the cross product of E and H is nothing but the Poynting vector S. And if you take the divergence of the Poynting vector S, that is, if you take divergence of S, you will get a scalar term. We'll call it the density of power flux PF. Okay? Why? Because you know that a divergence of any vector A is a scalar term. The curl of any vector A is a vector quantity, and a gradient of any vector A is also a vector quantity. Okay? Now since S is a vector quantity and you take the divergence of S, what you get is a scalar quantity, which is the density of power flux given by, denoted by small p subscript f, PF. Okay, now let's write it in a simple form, that del dot S is equals to del dot E cross H, because S is nothing but E cross H, which is equals to PF. Now this is written in differential form. Now since this is a divergence, we can again apply divergence theorem by doing triple volume integration on both sides. So if you do triple volume integration of del dot S d tau is equals to triple volume integration of del dot E cross H d tau is equals to triple volume integration of PF d tau. So we can apply divergence theorem on these two terms. So it will become closed surface integration of S dot ds, which is equals to closed surface integration of E cross H dot ds is equals to, let's call this a capital PF, because when we do volume integration of any density term, here we have a power density PF, so we will get a total power flux. This is total power flux. Okay, now we are going to use this or this in the first term of equation number 2 here. Now let's move on to term number 2 and 3 of equation 2, which is these two terms. We have to handle these two terms, then we can finally get the conservation of power equation. So this definition was for term number 1, and now we will attack term number 2 and term number 3 of equation 2. So for any medium which is linear medium in simple sense, for any linear medium in simple sense, we know that the total electric current density J total is equals to electric displacement current del D by del T plus the conduction current Jc plus the impressed current Ji, which is nothing but the source current, which can be further written as del by del T of, we replace the D with epsilon E and we replace Jc with sigma E, and Ji remains as it is. Now since we are dealing with medium which is linear and in simple sense, that is why we can substitute D with epsilon E and Jc with sigma E. Now what we need in the second term, we need something called E dot J total. So this is J total. If we can multiply E with this, we will get E dot J total is equals to del by del T half epsilon E plus sigma epsilon sigma E square plus E dot Ji. Now this half term comes because here we are dealing with the time derivatives. Okay. Again, for linear medium in simple sense, if we write the same equation for magnetic current M total, which is equals to del B by del T, the magnetic displacement current, plus Mi, the magnetic impressed current or the magnetic source current. Okay, now therefore if you substitute mu H in place of B and Mi remains as it is, and you multiply H on both sides, you will get del by del T half mu H square plus H times Mi. Okay, now let's call this as equation A and this as equation B. Now if you simply put A and B in equation 2, what we will get? We are going to substitute E dot J total and H dot M total in term number 2 and term number 3. So we will get del dot E cross H plus E dot J total plus H dot M total is equals to 0. So I am rewriting equation 2 once again. Now when you substitute equation A and equation B here, you will get del dot E cross H plus del by del T times half epsilon E square plus sigma E square plus E dot Ji plus del by del T half mu H square plus H dot Mi is equals to 0. Now if I rearrange this term, this in this manner such that you have del dot E cross H plus del by del T times half epsilon E square plus half mu H square and sigma E square in the left hand side, and you take the source terms onto the right hand side, you will get minus E dot Ji plus H dot Mi. Okay, now I am going to hold this equation for some time, and this is the right time to define few more terms such as the dissipated power and the electric and magnetic energy densities. So let's do that first. Now I am going to call this equation as equation number C. Now let's define electric and magnetic energy density of static fields. So define electric or magnetic energy density of static field. So according to the definition, we define WE as half epsilon E square. So you look at this term. This term is defined as the electric energy density, which is WE. Similarly, we will define Wm as half mu H square. So this term is defined as the magnetic energy density of static fields. Okay, now since these are density terms, these two are energy density terms. So if you do volume integration of these two terms, you will get the net electric energy and the net magnetic energy. So let's call that as capital WE is equals to half triple volume integration of epsilon E square. We will call this as net electric energy, and capital Wm as half triple volume integration of mu H square, and we will call this as net magnetic energy. Okay, next we will define one more term, which is dissipated power density. Dissipated power density. Okay, so this is also a density term, and we define it as small pd, and this is nothing but sigma E square. So if you see this equation number C, here this term sigma E square is defined as the power density which is dissipated as heat. It is defined as the dissipated power density which is dissipated as heat. It's a power loss term. It's the loss term basically. So now again, if you do triple volume integration of PD d tau, you will get triple volume integration of sigma E square d tau, and we will simply call this as capital P d, and this will be your total dissipated power or total power loss. Okay, all right. Now lastly we need to define supplied power density. Supplied power density, and that will be defined as small ps, which is equals to negative of E dot Ji plus H dot Mi. So this is the supplied power density term. Again, if we do triple volume integration of Ps d tau, we can write it as small ps, and this will be named as total power supplied. Total power supplied. Okay, so if you check this term, we are replacing that term with capital PS as the total power supplied, or the small ps, which is the supplied power density. Now if you simply substitute all these defined terms in equation number C, what you will find is that we have defined del dot E cross H as PF, density of power flux. We have defined half epsilon E square as WE, that is electric energy density. We have defined half mu H square as small wm, which is magnetic energy density. We have defined sigma E square as PD, that is dissipated power density, and we have also defined E dot Ji plus H dot Mi, this is negative outside, as PS, that is power supplied power density. Okay, therefore we can write equation C. What was our equation C? Let me rewrite that equation C once again. Equation C was del dot E cross H plus del by del T half epsilon E square plus half mu H square plus sigma E square is equals to minus E dot Ji plus H dot Mi. Now we will substitute these terms here. So we will get PF plus del by del T in brackets WE plus WM plus PD is equals to PS. Now in a more useful way, power supplied is equals to the power flux PF plus the stored energy densities, that is WE plus WM, and the dissipated power PD. So basically we have power supplied is equals to power flux plus the stored energy plus the power dissipated or the power loss. Okay, so what actually happens in a case of an antenna system is that, suppose you have an antenna, you supply some power PS, some of the power is dissipated as heat inside this antenna system, which is PD. Some of the power is stored inside the antenna, which is stored energy, electric energy, and stored magnetic energy, and the remaining part is transmitted away, which is the power flux PF. Okay, so what we usually are interested is on this part, that how much power is getting transmitted in the free space so that the signal can be transmitted. Alright, okay. Now again at the last, if we simply substitute with the total power and total energy, we can substitute this as PS is equals to PF plus d by dt times capital WE plus capital WM plus PD. So what we have done is, we have simply done triple volume integration on this equation, and we have got the total supplied power is equals to the total power flux plus the total electric and magnetic energy density plus the total power which is dissipated as heat. Okay, so this particular equation is called conservation of power at any point or within a region. Okay, so this particular equation, so let me call this equation as equation number 3. So equation 3 is conservation of power at any point or within a region. So remember that we have been dealing with fields which are instantaneous in form. So we were dealing with instantaneous field quantities, that is the scripted letters for E and the scripted letters for H. And when we will deal with the complex field quantities, then we will find that this equation number 3 has a little different form. So that we will cover in the second part of this lecture number 4. I hope you have understood this. Thank you.